Okay, everyone, this is Dr. Jackson again, and this is part 4 of the lecture that goes along with chapter 8, hypothesis testing 1. And so for this part of the lecture, we're going to cover I'll cover a couple of different things. Choosing a one-tail test. I will also talk about some of the different choices you have to make when it comes to um, doing a hypothesis test. I'll talk about the t distribution, and then I will, I think, wrap it up with proportions. Okay. So again, this is the part 4. I will try to get through this part within 30 to 35 minutes, but there are quite a few things that I do still need to cover. So if everything works out and I am able to have all of this in one more part, then the fifth part will be me going through and doing the demonstrations of the different hypothesis tests. Okay, so choosing a one-tailed or two-tailed test. Remember, this is one of those where up to this point, we have basically been doing things where we look at everything in both sides, on both sides of the normal curve. Well, that's not reality. That's, everything isn't going to always be on both sides of the normal curve. Sometimes you want to know things about whether something is higher or lower, all that different type of stuff. So I'll talk about that a little bit more on the upcoming slides. But there are some critical or crucial choices that the researcher has to make when it comes to hypothesis testing. And those choices are essentially based on the researcher's expectations. The first choice, is, do we do a one-tailed or a two-tailed test? And this is where the researcher is unsure about the direction, and the hypothesis will only state that the population mean is not equal. If the researcher is certain about the direction, then this is where they'll say, they'll give that information. And I'll show you that in a minute. The second thing that researchers have to think about is the alpha level, and what to set it at, how much risk they're willing to take. And then there's an additional concern that goes along with this that relates to something called type 1 and type 2 error. Okay, but first, again, this is choosing a one-tailed or two-tailed test. So this is basically, it's based on the researcher's expectations, like I just said. If the researcher is unsure about the direction, the hypothesis would state only that the population mean is not equal to um, what's being stated in the null hypothesis. So everything that we've been doing up to this point is basically two-tailed. All right. So just that would be one way to think about it. Um, Now, in a two-tailed test, excuse me, yeah, everything that we've been doing to this point is a two-tailed test. In a two-tailed test, the researcher is equally concerned with both sides or both directions of the normal curve. Essentially, the researcher is concerned with the possibility that the true population value is greater than or less than the value stated in the null hypothesis. So, hence, the researcher is concerned with either direction. However, if the researcher is only concerned with differences in a specific direction, or the direction of the difference can be predicted, that's a one-tailed test. So you can take, a one-tailed test can take on two different forms that demonstrate the direction of the test. And if the researcher believes the true population value is greater or less than the value presented in the null hypothesis, then what you see on the screen where it says H1 and then it has the mean is greater than 7.2, where the greater than sign signifies greater than, that's one version of the two-tailed, like the way you write a hypothesis for a two-tailed. The other version is if the researcher thinks that the population value is going to be less than, then like you see here, H1, and then in parentheses, you have the symbol for the population mean is less than 7.2, where the less than sign signifies less than. Yeah, that's essentially how you would write it. Now for the examples here, the two-tailed test is as follows. The null And this is the alcoholics in the community example. That's what I'm using for this particular example, if you will. So the one where it was the alcoholics, people who have received alcohol treatment, and we were looking to see if they were different from the community in terms of absenteeism. Well, the null hypothesis is that the population of treated alcoholics is no different from the community as a whole, because what you're looking at is are there differences or are there no differences? The difference between a one-tailed and a two-tailed test is basically you are talking about the type of difference. In a two-tailed test, you are only looking at, is there a difference in general? So again, the null hypothesis for a two-tailed test is that the population of treated alcoholics is no different from the community as a whole. In the alternative or the experiment hypothesis, so that's the second one, that's this one right here. Yeah, that's this one right here. Uh-oh, I covered it up a little bit. So this one right here, the alternative or the experiment okay. Well, third time's a charm, folks. There we go. Not quite a circle, but close. Yeah, so in the second one, we're basically saying that the mean is not equal to 7.2, that there is a difference, okay? The hypothesis is basically that the population of treated alcoholics is in fact different from the community as a whole, but we're not saying what direction. In the one-tailed test, it goes as follows. You would say that you would have the null hypothesis. So this is going to be the same regardless. So the null hypothesis is going to be the same regardless of if you have a one-tailed or two-tailed. Your null is always going to be, let's see if I can write this. Your null hypothesis will always be there we go. So your null hypothesis is always going to be HO, so the H subscript O, the mean sign is equal to whatever your number is. It's going to always be that. All right. So over here, I'm going to try this again. Over here, if we have a one-tailed test and we say that we are writing it out, we would write out for the null, we would write out we would write out HO and then the population mean equal to 7.2. Then depending, I know that looks really horrible. You probably are like, what is that weird looking symbol? That is supposed to be the population mean. Let me try writing that again. I'm just going to do a normal n is equal to 7.2. That's what that is. So just imagine that is the symbol for population mean. That's what the null hypothesis would look like, whether it's a one-tailed or a two-tailed, okay? But then your alternative hypothesis would be one of these two. So in this first example, the hypothesis in this one-tailed test is essentially saying that treated alcoholics had higher absentee rates than the community. Another way to say this is that the treated alcoholics average more than 7.2 days of absenteeism, okay? The second version, that's this one right here. So number 2, so this is the second version. This is number 1. I'm getting ahead of myself. Okay, so number 1. All right, so number 2, what's being said here, in this one, the one-tailed test is essentially saying that the treated alcoholics had lower absentee rates than the community. Another way to say that is that the treated alcoholics averaged less than or fewer than 7.2 days of absenteeism. So let's say that I wanted to go with H1, because this is still going to be the same. These are just two different versions of saying the same thing. So I would essentially write it out as okay. So let's say that this right here was my part of my hypothesis test. That's essentially what it would look like. You have your null hypothesis at the top, and then you have your research or your alternative hypothesis there at the bottom. But in a one-tailed or a two-tailed test, you have the greater than or equal to sign. And your question is going to have, there's going to be something in the question, that gives an indication of what direction you need to go in. All right, so what I want to demonstrate here is something, just kind of reiterating the point that up to this point we have been using. We've essentially been using the two-tailed test. We've basically used z-scores that cover both sides of the normal distribution, and that's why I have, some of you may recognize this as the table from chapter 7, where it shows you the alpha divided by 2, and then it gives you the z-score. Well, take a look at these numbers, okay? And then I'll do that one as well, because that's one of our most common ones. Well, z-score, and remember the alpha in this is divided by 2, because we had to divide and account for the fact that the alpha was covering 2 different regions. Well, if you look, you'll see that those numbers correspond to the two-tailed value for one and two-tailed tests. All right. So the alpha at the 0.10 level is the same as what we've been using. Same thing with 0.05. All right. Now it's where we get to the one-tailed test. That's when things change. Okay. Those numbers are going to still be the same. You're just dealing with plus or minus. But the alpha for a one-tailed test, the z-score for a one-tailed test is no longer 1.65. You got to look at these numbers right here. It's 1.29 for an alpha of 0.10. The z-score has now changed when it's a one-tailed value. Remember, for alpha at the 0.05 level, which is the one that I always tell you is the most common one used in sociological research or social science, well, that z-score is no longer 1.65. It is no longer 1.96. It's now 1.65. So on and so forth. So these numbers that you see up here that we've been using, okay, the two that you've been using the most are the 1.65 and 1.96. Those numbers go along with the two-tailed value. The one-tailed value, the numbers are going to differ. So if you have a one-tailed test, you need to look at this so you can see what those numbers are. I would definitely suggest having this table, okay, this bottom table, this one right here, where it says finding critical z-scores for one and two-tailed tests. I would have this table somewhere near you when you work on these problems, because once you figure out what direction what kind of test you're doing, if you're doing a one-tailed or a two-tailed, you need to go to the table, find the alpha level, and then find the z-score that's going to correspond. Okay, that would be one of my suggestions to you. Let's see here. I think, one of the other things when it's a one-tailed test, depending on the direction, that's what's going to determine whether it's plus or minus. Okay. So typically, if you're dealing with something that's less than, you're going to have the negative. If you're dealing with something where they want to know, are you looking at something that's larger or greater than whatever it is you're doing, you would have a plus. You don't have to write the plus if it's positive. The only time you need to do the sign is when it's a negative one. Okay. All right, so, oh, real quick, this particular table right here, that is on page 197 of the textbook. Okay, it's table 8.3, which is on page 197 of your textbook. This particular table, this is just, since alpha at the 0.05 level is the most common, this table was also included. So it's basically just telling you, giving you information of if the research hypothesis uses whichever one of these. So if it's and research hypothesis, remember, that's the hypothesis that you come up with. This is not the null hypothesis. The null hypothesis is always going to be the population mean equal to whatever the number is that you're looking at. Okay, so if you have the equal sign with the line drawn through it, that means not. That's basically saying your mean is not equal to whatever that number is. That's a two-tailed test. But if you have a greater than or a less than sign, it's a one-tailed. And what this is telling you is where you need to look and the type of Z critical you use. And they're doing this for alpha at the 0.05 level, because one, that's the one we use most common. But you could actually do this and make something like this for alpha at the 0.10 level. You would just have to make sure you put the right information in. All right, so what this, along with the next two normal curves, they're just demonstrating where the critical region will fall for the two-tailed and the one-tailed test. So and this is for when you have alpha at the 0.05 level. As I always say, you should draw these tables out when you work on these problems. Something that I tend to do is I'll use or print multiple copies of a blank normal curve. Like if I have the ink and the paper, I'll print them off. Or I'll print a bunch of them. Like I might print 2 on one paper, 3 on a paper, and then I'll number whatever the problem is and draw the stuff out. If you guys notice that a lot of times when I am going through and doing some of these problems, especially when I was doing the normal curve stuff, and I think I did this when it was the confidence intervals, I actually had pictures or copies of blank normal curves, and then I would fill in the information, because as you guys have already seen, I can't draw these curves. I have a hard enough time writing stuff in a straight line when I'm doing this, so having to draw out all those curves would not be it would be problematic, I'll just say that. But go ahead and do that. That would be a good way to make sure you do this, because sometimes people just forget. But if you have that little table there, or the normal curve, the blank one, maybe you'll remember to do it, and then you'll see where things fall. Now, this particular slide is basically demonstrating the critical region for a two-tailed test with an alpha level of 0.05. And as you can see, actually, I'm going to use the pen for this. As you can see, here is, because remember, it's two tails, it's plus or minus. So we've got the minus over here. We've got the plus over here, and everything that falls here in this area, that is our critical region. That's where we want our Z obtained to fall. Okay, so everything that I'm coloring in black, that's the area beyond the Z critical, if you will. Okay, so if your score falls in here, or if your score falls here, then you reject the null. But if it falls in this area right here, you would accept the null. So reject, accept the null. Basically saying there are no differences. Okay. All right. So what does it look like when you have a one-tailed test? Well, here's a one-tailed test, but it's in the upper region. So if your Z critical, if whatever you're doing is not whatever you're doing, if you get a question and it basically wants to know that if the hypothesis is that the population mean is higher than the value stated in the null hypothesis, that's what this would be. Okay, so this area shaded in blue, so I'm just going to circle it. This area right here, shaded in blue, is the critical region. And if your Z obtained falls in that region, you reject. Okay. If your Z obtained, falls anywhere over here, so if your Z obtained falls in anything going in this direction, you accept the null. Okay. Because in this instance, you want to know, is the population, do you want to know if the hypothesis that the population mean is higher than the value stated in the null hypothesis, you want to know if that's the case. Well, if it does, it's going to fall over here. Okay. It's going to fall in this critical region. And it's the exact opposite when it's a one-tail test for the lower tail. This is what the normal curve would look like if the hypothesis is that the population mean is lower than the value stated in the null hypothesis. So again, this area right here, shaded in blue, that's what you want. That basically means you reject the null. All right, but if it's everything other than that, so if it's everything on from this side on or going in that direction, or all this over here, and it falls in this area, you accept the null. All right, so that's essentially what it would look like and what that means. All right, so remember I said that there are two critical choices that a researcher must make when conducting a 5-step model. Well, this is the second critical choice. They have to look at the alpha and they have to decide on which alpha they want to select, because that has an impact on the probability of being wrong, the risk that they're going to be wrong. Okay, so it's important for that reason, but it's also important because if you select the wrong alpha, you could run the risk of, if the researcher selects the wrong alpha, they could run the risk of making what we call type 1 and type 2 errors. So even though researchers will work really hard to ensure that they don't mistakenly reject the null hypothesis that is true, or fail to reject the null hypothesis that is in fact false, it's still possible to make these type of errors. And these are errors called type 1 and type 2. So a type 1 error basically refers to the error of incorrectly rejecting the null hypothesis, which put differently means that you reject a null hypothesis that is true. So that might sound like a little bit of a tongue twister to some of you, or it might just be confusing, but this is essentially what it means. It means that the researcher has found statistical significance and they've thus rejected the null hypothesis. Put differently, the researcher has conducted the hypothesis test and found that there were statistically significant differences in the groups when in fact the opposite was true. So basically they've said my research hypothesis is correct. So an example would be, think about the treated alcoholics example for the two-tailed test. In this example, we basically rejected the null hypothesis and accepted the alternative experimental hypothesis. So we said the null hypothesis that the population of treated alcoholics is no different from the community as a whole. We rejected that and we said that no, they are different. That population of treated alcoholics is in fact different from the whole community. Well, a type 1 error means that you got it wrong, when what you should have done was accepted that null and said, no, there are no differences between the community and the sample of treated alcoholics. Okay, that's essentially what it's saying. So that's a type 1 error. Type 2, basically refers to the error of failing to reject a null hypothesis that is in fact false. So type 2 error is essentially the opposite of type 1. Type 2 error essentially means that the researcher did not find statistical significance and therefore did not reject the null hypothesis. Now, put differently, this is basically the researcher has conducted the hypothesis test, found that there are no statistically significant differences in the groups, when in fact the opposite is true. So again, let's refer back to the treated alcoholics example for the two-tailed test. And let's say that the researcher didn't find statistical significance and failed to reject the null hypothesis, okay, which is basically saying the same as we accept the null hypothesis and you reject the alternative. Well, a type 2 error is basically when you got it wrong, you got it backwards. If we've committed a type 2 error, this means that we are wrong to say the population of treated alcoholics is no different from the community. Instead, we should have accepted the alternative experiment hypothesis and said that the population of treated alcoholics is different from the community. So again, like I was saying, type 1 error and type 2, they're the opposite of each other. All right. Now, hypothesis testing will always carry some form of risk. That's just how it goes. We can't really minimize both types of error at the same time. And this is because as the probability of one type of error goes down, the other type goes up. So for instance, as you decrease type 1 error, the probability of committing type 2 error goes up. The best we can do is try to select an alpha level as a way to balance out the two types of error. Now, keep in mind that higher alpha levels will minimize the probability of committing a type 2 error. And lower alpha levels, this would be levels of 0.05, 0.01, 0.001, those will minimize the probability of committing a type 1 error. And typically in our field in criminal justice and juvenile justice research, we want to minimize type 1 error, okay? This is actually a norm of social science research. And this table down here, basically what the table is giving you, it's giving you a decision-making model. It's a way to kind of help you visualize what they're talking about with the two different types of errors. All right, so I'm actually going to keep pushing on. We're at about 27, 26 minutes at this point, but I don't want to make a million videos. So at this point, if you need to take a break, this would be a good time to pause and then come back. All right, so the student's T distribution. Basically what this is, in the lecture for chapter 7, we dealt with examples where the sample was large. And up to this point, we've been dealing with those types of samples. And that allowed us to use the sample standard deviation when the population standard deviation was unknown. Now, you may remember that I briefly referred to the student T's distribution when I was talking about the different types of sample sizes and small samples versus large samples. If you don't remember, that's fine, because that's what we're dealing with right here. And I'm going to discuss this in more detail. So basically, if you have a situation where the sample is small, the N is less than 100, you don't know the population standard deviation, and you only have the sample standard deviation as an estimator of the population standard deviation, you can't use the standard/normal distribution. It doesn't work that way. The whole point of the standard normal distribution curve, so that's the Z, okay, the Z table, the Z distribution. The point of that is we're dealing with sampling distributions. And as you start having more and more numbers in your sample, the larger your sample gets, the closer you get to the normal curve. So remember, the standard distribution is based off of, it looks like the normal curve. Instead, what'll happen is if you have a sample that's small and you don't know the population standard deviation, this is when you use the student T's distribution, which is on page, it's appendix B of the textbook. All right, so what this is right here, this figure is also on page 203 of your book. It just demonstrates that for small samples, the T distribution is flatter than the Z distribution. But one thing to keep in mind is as the sample size increases, the T distribution begins to resemble the Z distribution. So once the sample size becomes greater than 120, the T and Z distributions start to become identical. So, and that's why we look at, samples of a certain size. And that's kind of one of the things why when a sample starts to get over 100, you can theoretically, you can use the Z distribution, but anything less than 100, so 99 and below, you need to use the T distribution. Now, one of the things that you might want to do, I'm always telling you, put stuff in notes, print things out, have yourself a little booklet of things that you can flip to, but use this as a guide to determine when to use each sampling distribution. There are a variety of methods you could use to organize the information relevant to choosing the sample distribution. So whether you use the T or whether you use the Z distribution, there are a number of ways you can organize it. You do what works best for you. But one of the things that I thought about, you could create a set of note cards, physical or virtual note cards, or you could do a PowerPoint slide. Like maybe you take a slide similar to this and you have the information that you need that lets you know the formula, the distribution you use, and all of that type of stuff. I would say put the formulas you need, even if they're the same across the board on each card. So you have a card that's maybe student T's distribution, and on that you have information. If sample is less than 100 and you don't know the population standard deviation, use the T distribution. You may, and then you have the formula that you need, that all the formulas you need to do a hypothesis test. However you choose to set that up, that's one way to go about it. And then this way, once you figure out which distribution to use, you only need to look in one place for the information related to that distribution. Another tip would be maybe create a flow chart. And so what I mean by that is maybe you have a chart where you start off with, if maybe it starts off with, you have your sample. So like something like this, maybe you have a sample number, or you have your information, and then it goes off to the side. If N is less than 100, then you follow these steps. Then it branches off. If such and such does this, and you could do it like that. We call them flow charts. Some people call them process charts. That might be something that you can do, but whatever will work for you to help you organize this information, and yeah, whatever's going to help you organize this information, right? So let me just do that again using these as examples. So let's say you have a box, whatever, and you have your N, you have your information. So let's just say the N is less than 100. Oops. All right. So the N is less than 100. And you have an N less than 100, and your sample size is, I'm sorry, I did that backwards. Apologies. Let's say, because what I'm actually looking at is the standard deviation. That's what I want. So let's say in your box, you have a standard deviation, and you start off here with whatever information from your problem is, and the standard deviation is, let's say they give it to you, and the population standard deviation, they give it to you, and it's 2.5. Then, so basically you're looking at that population standard deviation is known, then you use the Z distribution, okay? But let's say you have a problem where you're creating a little map for yourself, and it is, all you have is the sample standard deviation. So S equals 1.2, but population standard deviation is NA. So we'll just say NA, you don't have it. Okay, so then over here to this side, if you know that you look at your N, and if your N is greater than 100, you know that, I'm going to use the Z distribution. Over here on this side, if you your N is less than 100, you know that you need to use the t-distribution, okay? You know, that for some of you, you may be like, I don't need to do all that, but some people are visual and that might be what helps you, okay? So, you know, do what you need to do to help you get through this information. All right, so the students T, basically, you can look at page 203 of the textbook for a more detailed description of these differences. But Appendix B, it's on page 447 of the textbook. And so the table that you see here, this one right here, so this table right here, let me just do this. This is not the table that's in the back of your book, but it looks just like it. The only difference between this table and the one in the back of your book is this number, right? This item right here. For those of you, if you're having a hard time seeing that, that basically is N minus 1. But for our book, I think it's N minus 1. The book, but your book doesn't actually state this. So that's the main difference between the two. Is the course textbook does not give you that N minus 1 on there, okay? But everything else essentially looks the same. So let me go through, highlight, and demonstrate what I'm talking about here. All right, so in this table, and as most of you can see, it completely differs from the Z distribution. What you're going to do, you need to know the degrees of freedom for whatever problem you're looking at. And that's what this is right here. So degrees of freedom, that's this first column right here. So that's what this is. That is your degrees of freedom. You need to know that. That's going to be the number in your sample minus 1. So that's what this is over here, where it says it's column at the left for degrees of freedom. That is the number in your sample minus 1. So I think for the treatment of alcoholics, I think that number was 117. So you would take 117 minus 1. That's your degrees of freedom. And what you do is you find it in the table. Okay. All right. So then up here, you have to look at, this is where you need to figure out, are you dealing with a one-tailed test or a two-tailed test? The one-tailed test, that's this top row. All right. That is the top row. Let me change that color. So this is this right here, where I'm drawing this blue arrow, that is your one-tailed test. Now where I'm going to draw, I'll draw a red arrow. This red arrow, that is your two-tailed test. And what you're going to look at are these numbers right here. Okay, I don't know how well you can see those, but these numbers right here. That's what you're going to look at for the two-tailed test. For the one-tailed test, you look at these numbers. Now, your course textbook does not have the numbers for 0.5 and 0.4 or 0.3. If I remember correctly, your textbook starts with the 0.20. So these first 3 columns, they're not in your textbook. Doesn't mean that they're not valid. It just means that it's not in your course textbook. But you can always go find a T-table kind of like this one, and or you could use this one actually. But most of the problems you're going to have, they're going to look at levels of significance that start here, because remember, we don't really look at anything above anything like that. We go to 0.1 and typically 0.1. Okay. All right. So that's essentially what you have going on with this table. You find the degree of freedom, you find it here. So you go to whatever that row is. So let's say the degree of freedom is 11. Yeah, I think that's what that says. Let's say it's 11, and I know I'm dealing with a one-tailed test with a significance of 0.05. So if I'm dealing with a one-tailed test with a significance of, so that's right there, significance of 0.05, and my degree of freedom is 11, I'm going to track all the way over to this number right here. Now, for me, this number is really small, so I can't see it. I think that says 1.796, I think is what that says. So that would actually be my Z critical. And, you know, this marks the beginning of the critical region, not the area under the curve. All right. For a two-tailed test, you do the same thing, but instead of looking at, so remember, for a two-tailed, it's 0.05, and it's this column. But if it's a, I'm sorry, one-tailed, but if it's a two-tailed test and I want 0.05, I come over here to this column, okay? All right, so at this point, this is the last section. One of the things that I'm not going to do is demonstrate the go through an example with the T distribution, because those 5 steps are exactly the same as a Z distribution. The only difference between those two types of problems is instead of using a Z obtained and a Z critical, you're using a T obtained and a T critical. And the number that you find, the number that you use, you pull it from different charts. So that's really and truly the only real difference. So again, the 5-step model is the same with the student T's distribution as it is with the Z distribution. So again, I'm not going to put an example problem up here. You know, we're already at about 40 minutes into this particular lecture, part of the lecture. And instead, when I do examples in part 5 or the 5th video, you know, that's when I'll go through and demonstrate the problems. I'll demonstrate some problems from the book. All right, so at this point, I have been going for about 42 minutes. I think this part may take me another 10 minutes or so, maybe a little bit less time, depending on if I do one of the calculations or not. So if you need to go take a break, now would be a good time to do so. Because I'm going to go, like I said, for another 10 minutes or so. Okay, for those of you that are not going to take a break, or those of you that have come back from the break, if you pause the video and you come back, we are now going to look at proportions and the 5-step model. So the steps themselves are more or less the same. It's the formulas and the interpretations that are different when conducting a hypothesis test for proportions. So I've included the 5-step model for proportions so you can see those differences. There are times when we don't use interval ratio variables, but we still need or want to conduct a hypothesis test. In instances such as these, it's inappropriate to use the mean. Instead, we can use the sample proportion as the test statistic. So again, the 5 steps are essentially the same, but there are some key differences. Now, the key differences or changes to the 5-step model for proportions, basically, if you go to page 208 of the course textbook, this is where you'll see a more detailed discussion of these changes. But in step 1, instead of assuming the variable is interval ratio, we assume that it's measured at the nominal level. You still have the part about it being random, and you still have the part about the sampling distribution, but instead of interval ratio, we say that it's a nominal level of measurement. And because we're using proportions, the symbols are going to change. So now we're no longer using the symbol for the population mean. You know that M, that odd looking M that I can't write? Well, we're not using that anymore. Now we're using the symbol for population proportion and the population sample proportion, you know, or whatnot. In step 3, the book mentions that we will only use the Z distribution because the small sample tests for proportions are not considered in this particular textbook. So to be consistent with the book and to avoid confusion, I'm going to do the same thing. I'm not going to introduce or talk to you about small sample proportions. And then step 4, the symbols in the formula for the test statistic change because we're using a proportion. I think I wrote this wrong. I meant to make the change because I didn't put the information for step 3 up here. And so when I was looking at this, I forgot to go through and change this so that it says step 4. Okay, so let's just, we'll black that out. So for those of you that are writing this, just know that that is step 4. Okay, so this is the change to step 4, not step 3. Okay, my apologies for that. I hope that doesn't cause any confusion. I'll try to make sure it's changed on the PowerPoint, the PDF of the PowerPoint. I'll try to make sure it's changed there. But this formula, the formula for Z obtained, that is step 4. Okay. All right, so again, this is a categorical variable. The household is either headed by a woman or it's headed by a man. Remember, nominal level variables have non-numerical scores. So in other words, there's no numerical value to the variable. You can't put a numerical value on being male or female. The only thing you can do is count the size of the categories and make comparisons. So for instance, here we have the count. Here we can count the number of female-headed households, which based on the information in the problem is 53. We could then compare the number of women-headed households to the number of male-headed households. So, but what we're interested in is whether the sample proportion is different from the population proportion. So what we'll do is conduct a hypothesis test for a single sample proportion. And this problem tells us to do it at the 90% level. So you'd have an alpha of 0.10. Now, before we begin and move on to step 1, you need to get 2 pieces of information. You need to get that the P subscript S, and you can, I don't know if you see that here, but it's highlighted in purple. Or it's in purple text, excuse me. But here's the P, the PS, and here's the number for it. And if you're wondering, well, how did you get 0.43? That's basically you take the number that you're looking at and you divide it by the whole group. So 53 divided by 122. So the proportion of women-headed households is 0.43, okay? We also need to determine the Z-score that corresponds to the alpha. And this is where, in order to do that, you have to determine, is this a 1 or 2-tailed test? Well, this question only asks if the households in low-income neighborhoods are significantly different, okay? They're only asking if those households are significantly different. And remember, if it's only asking about a difference and it's not telling you higher or lower or anything like that, that's a 2-tailed test. There's nothing here that suggests a direction. The question does not ask if there are more women-headed households and low-income neighborhoods than there are in the city as a whole. If that were the question, then we'd have a 1-tailed test. But since the question is only asking whether the sample proportion is different from the population proportion, and we know there's no direction specified or predicted, we can conclude that this is a 2-tailed test. Then we have to determine the Z critical for a 2-tailed test with an alpha set at 0.10. And that's going to be plus or minus 1.65. Now we can begin the process of the 5-step model. All right, so the information you see in purple, this is what you would put in the write-up of the hypothesis test. And when I go through the practice demonstration problems, I will do all of that. I will write it out the way you would write it out when you're doing it. So I'm not going to go through all of these other than to point out, notice that here in step 1, with those assumptions and meeting the test requirements, we have a level of measurement that's nominal, okay? All right, so for step 2, you state the null hypothesis. So this is the population proportion, is equal to 0.39. Whereas, excuse me, the alternative hypothesis is that the population proportion is not equal to 0.39. So in other words, the difference between 0.43 and 0.39 is trivial and caused by random chance. So the null hypothesis is that the two scores or the two groups are equal, they're the same. Whereas the alternative is basically that this difference where we got from our sample of 0.43, it's actually different from that 0.39. There is a difference between the lower income households and all neighborhoods. And again, what you see here in purple, this is what you would write up in the actual hypothesis test when you're writing it out. All right, so step 3. I know I'm moving through these a little bit quickly, but because the steps are essentially the same, it's just some of the information is what changes a little bit. That's why I'm not going into as much detail with these. All right, so for this is actually how it would look when you write it up. The sampling distribution equals Z distribution. So you write that out. You say which distribution you're using. Is it the Z distribution or the T distribution? Then you have your alpha. You say what your alpha is, and in parentheses, write out, is it one-tailed or two-tailed? Because then that'll help you remember or help you go look at the Z critical. And because it's two-tailed, you know you need a plus or minus 1.65, okay? Now, initially I was going to calculate this out and walk through the steps. You know, you guys know I like to do that. However, I'm not gonna do that this time. I'm not gonna do that simply because we're already at 51 minutes. And if I go through and calculate everything, that's probably gonna be another 5 minutes or so. So I would suggest you go calculate it out yourself. However, don't rely on what you see in the book. Those of you that read through the book, you know that this question actually comes from the book, or this problem comes from the book. Well, the book doesn't quite have it correct. I'm not sure what was going on when they did this, but there's a mistake. If you practice this problem out and you want to see if you get the same thing that I got, what you need to do is, let me write this out. Let me get the pen. What you need to do is calculate. So on one of the other problems, I calculated everything. Let me come over here. So what you want to do is calculate everything. When you're calculating everything, let me say that differently. When you're calculating everything, so when you're doing the calculations, round to the third decimal. Then okay, there we go. Then when you get to the final answer, round the final answer to the second decimal place. So if you need to take a moment, pause and write this down. But calculate everything that you see in the problem to the third decimal place. So when you get this number down here, or when you get these, like once you multiply this number needs to be rounded to the third decimal place. Then when you divide the number that comes out of this calculation, when you divide that by the 122, that number needs to be rounded to the decimal place, the third decimal place. Whatever this number is, you divide it by that number that has been rounded to the third decimal place. And then you should get 0.8888, and then you round that up to 0.89. So test it out, see if it works. And yeah, because what they get in the book, the way they did everything, if they did it the way it's shown in the book where they round to the second decimal place, their Z obtained should have been 1. But in the book, they have that it's 0.80. And I've gone through, calculated. I even went through and used Excel to round my numbers down, trying to figure out how they got that number. And that's one of the reasons why I say it's always good to write out your steps, okay? So you can see where mistakes are made, or I can see where mistakes are made, okay? So go ahead and try that. This one you can try on your own, because again, you'll get to see me do a whole bunch of problems in the next video. All right, so we are at the last slide, folks. This is step 5. This is where you make your decision, and you say whether or not you're going to fail to reject or whether you are going to reject the null. Now, remember for this one, remember our Z, let me go back. We said that our Z critical is 1.65, right? Okay, so let's come back over here. Our Z critical is 1.65, so let's remember that. So our Z critical is equal to 1 plus or minus 1.65. Our answer, okay, I forgot, my apologies, you guys. I forgot to go and change the number that they came up with. I forgot to change that. So it should be 0.89, but it actually doesn't matter because either way, the 0.89 is, it doesn't fall into the area. It's not beyond the critical region, because if we go and we draw this out, again, this is why we draw out the curve. Mine looks a little crazy, but that's okay. All right, so let's see here. So we'll say 1.65, 1.65. Let me look at something real quick. That number it's positive. Okay, so our Z obtained would be somewhere right in here, right? So that's going to be that 0. Let me write it up here. I can't write it down there. Okay, so 0.85. Okay, I don't know if you can see that, how well you can see that, but as you can see, the 0.85, the red line, which is our Z obtained, it does not fall in this region right here. Okay, it doesn't fall over there. So we fail to reject the null. And basically what we're saying is this population of women-headed households and lower income neighborhoods, they're not really different from the city as a whole. That difference that was found is really just due to chance, is what this answer is in this particular question. Okay, so that wraps up hypothesis testing. These have all been some really long videos. So what I would suggest you do at this point is take a break, and then come back and watch the 5th video, which is one where I will go through the problems. I'm not sure how long that's going to take. It may be another really long video, but take a break, because if you've watched this one all the way through, you've been sitting here for about an hour, and your brain may be on fire. So take a break and then come back and start practicing. Okay. All right. See you in part 5 when I demonstrate and practice some of the problems.